Consider another consequence of this high-speed rotation. Here is a thing called a governor. There is a sleeve here on a vertical shaft, and if I spin this system fast enough, you know what will happen. The spheres will move in this fashion. The sleeve will move up on the central shaft, and it could well intercept a valve here, which would shut off fuel to the motor, and that's why it is called a governor. Oh, notice I'm pretty nearly on dead center. There it is, there it is, there it is, there it is, a governor. Here is one that you can do, utilizing this fictitious force of centrifugal stuff. Here is a coat hanger, and here is a coin, a penny, the lowest coin of the kingdom, I guess, and I'm going to put that coin at rest on the bottom part of the hanger, and I'm going to swing this hanger with the coin on it in a vertical circle, and I say I can keep the coin there. Why? The coat hanger will exert a force on the coin just as the string exerted a force on the ball to keep it moving in a vertical circle. Watch it now. Somebody says, well, I hope it doesn't work, Professor, because, you know, well, if it doesn't work, then I've lost my professional dignity, but there must be a reason why it doesn't work if it doesn't. And remember, we don't ever say that the experiment failed. Watch it. Oh, it did go around 2 or 3 times and then flew off. Let us consider now another classic, which is really quite astonishing. Here is a glass tube through which a string passes. And I have named this demonstration the string in the glass tube. Notice the elegance of that. A string in a glass tube, I've named it the string in the glass tube. Now here on this end of the string is a little 10-gram weight, and here on this end of the string is a 100-gram weight. Now you know that 10 grams can't hold up 100. Of course not. 10 cannot hold up 100. But I'm going to do something to the little one and thus give birth to a strange force which will hold up the 100. Watch it. There we are. There we are. The 10 is holding up the 100. Indeed, I'm going to make it lift the 100. There it is. Oh, I'll do it again. There it is, lifting it. Now we must never say that there is a force radially outward on this thing pulling on the string. Oh, wait a minute. I said something wrong, and I'm glad I did, because it may lead some of you to catch me up on it. I said there is no force radially outward pulling on the string. Yes, yes, yes. There is a force which the string exerts on the body, and there is a force which the body exerts on the string, but there is no force radially outward on the body. So you see, ladies and gentlemen and boys and girls, in the heat of this argument, I could very well make an utterance which the good people will quickly detect. And I'm glad I detected it, so you will see that there are occasions when I say things that are not right. Consider another of this business called centrifugal force. Here is a flexible loop which happens to be of rubber. I sometimes use a chain. Very flexible. It hangs quite limp-like. Now what do? I put it on a circular disc, and I rotate that disc at very high speed on a rotator such as I had here. And then I trip off the chain or the loop. Now look what happens. There is the circular disc. Here's the chain around it. And I bring this up to a high speed. And I trip it off. Remember, the chain was a limp structure. And what does it do? It rolls away as a rigid, solid iron hoop, for reasons which I leave to you to explore. Now, since I am given to the physics of toys, I ask you to consider another interesting little thing concerned with rotational motion. Here is a little toy which can shoot a hoop. A hoop. I will not reveal any of the secrets, But there is a rubber band which can give rise to a torque to turn the hoop. And, well, notice, it was an accident, but that's all right. I'm going to shoot the hoop away. Question. You will see the hoop roll away, and then you will see the hoop roll back. Or have I said it correctly? Let me invite your attention to this enchanting little business. Watch it. There it is. Now I'm going to do it again because I like it. And if I like it, that's reason enough to do it. Watch it. There it is. There it is. And I want to know what is going on. So you see, boys and girls and ladies and gentlemen, another bit of my philosophy here, my instructional philosophy. It is not always to answer the questions, but to raise some interesting dilemmas. Why things are so. Why things are so. Now, let me see what else we have here. I am not a cowboy, but the question arises. How is it that a cowboy can make a lariat or a lasso, L-A-S-S-O, often mispronounced lasso? How can a cowboy make the thing go in a circle, in a ring? Well, there it is. Notice the circular shape it took up. And the question arises, why is it circular? Interesting. Dilemma. A jug of water. Do you see again, ladies and gentlemen, and boys and girls, again some more of my philosophy. I use often the most plebeian and humble and simple and trivial things to demonstrate these wonderful properties of nature. How can I most quickly empty this jug? Watch it. There it is. And I thank you for giving attention to our business. This is the quickest way for the water to come out of the jug.